Without further ado, let me introduce our first speaker of the day. Scott Aaronson is the TIBCO Career Development Associate Professor of Electrical Engineering and Computer Science at MIT. This year, he received the Alan T. Waterman Award from the National Science Foundation in recognition of his work on computational complexity, which explores the limits of quantum computers. He has also received the Junior Bose Award for Excellence in Teaching from MIT. And so welcome very much, Scott.
Okay. All right, well, thank you so much. It is great to be back here in the city of my birth, and it's it's also I'm very impressed and and honored to be able to speak at your year on proof. Any university that would devote an entire year to proof is okay in my book. So. So I want to tell you a little bit about some new notions of mathematical proof, proving without explaining and checking without understanding. All right, so I guess you all already looked at this slide, but for most of history, a mathematical proof meant sort of a demonstration, in words, formulas, pictures, that it may require a whole process. It may have several steps, but the understanding that it produces is sort of a subjective thing. It's in the mind of a human mathematician who perceives it, and usually it sort of comes all of a sudden, right? You either see it or you don't, right? And once you see it, you're sort of you're certain that the statement is true. Okay, a classic example would be, here's maybe the most common proof of the Pythagorean theorem there is, right? Where you say c squared, or you can calculate it as the area of the larger square minus the area of the triangles, and then you get a squared plus b squared, right? You just you look at the picture, and and there it is. Now of course this is it sort of, you could say, well, what if someone doesn't see it, right? Of course, what has made this work for, millennia, in the history of mathematics is that, the mathematical community, seems to be able to reach consensus, in almost every case about, if not, what is or isn't a proof, at least, what could be made into a proof, right? But you can see that there is something a little bit subjective here, right? There's it's not obvious in particular how you would program a computer to recognize this sort of proof, right? Or how you would make it a completely mechanical process. We're still defining proof by what a human mathematician would recognize as such. But now, beginning in the late 1800s, I'd say, and continuing through the early 20th century, sort of a new notion of proof sort of emerged into the world. Names associated with this are Frege, Hilbert, Russell, Gödel. Okay, and probably, many of you know this story, but, the way that I would summarize it is that people, started to realize that proofs could be considered mathematical objects in their own right. Okay, so there's a second kind of proof, if you like, than the kind that human mathematicians show each other on the blackboard. Okay, which is a much more formal kind. And the second kind is a string of symbols that, in some sense, mechanically certifies that a theorem is true. Okay, and usually the way that happens is that you start from certain agreed upon axioms, like maybe the Peano axioms or the Zermelo-Fraenkel axioms of set theory, and then you apply certain agreed upon logical deduction rules. Okay, each of which is individually very simple, very innocuous looking, in order to just derive a sequence of new statements, starting from your axioms, and then if eventually at the end of this you reach the statement you're trying to prove, well then your statement was true. Okay, here is an example. This is actually the proof of what was called the Robbins conjecture, that says that all algebras that satisfy a few axioms are Boolean algebras, have have just two elements. And this was actually conjectured in like 1933. Tarski gave it out to his students for years and years, and none of them solved it. Finally, it was solved in 1996 by actually a computer search that just searched through all billions of different derivations from the axioms until finally it reached the axiom. It reached the conclusion that said, yes, this thing is Boolean. Okay, and as you can see, the proof is not actually that long. I've just reprinted it there. Right, once the computer has found it, in this case, a human can just go through line by line and see that it all checks out. But it's not clear that a human would have come up with this thing. Okay, and certainly it doesn't give you any particular insight or understanding as to why the statement is true, right? It just sort of tells you that it is true, right? And here's the logical derivations. Okay, so already you see both some of the advantages and the disadvantages of this formal concept of proof. The great thing is you can program a computer to check the proof for you, okay, which is wonderful for sort of things like software verification, which is a major application area for this sort of proof today. Okay, sometimes you can even program your computer to find the proof for you. Okay, that obviously is a lot harder, just because you have a combinatorial explosion in the number of possible proofs that you would have to check. Okay, but sometimes, like in this case, you can also do that. Okay, the disadvantage is, well, it doesn't give you a lot of insight or understanding. Furthermore, formal proofs of the property that they can sometimes be absurdly tedious. Okay, so in the lore of mathematics, right? There's one of the the famous things is in volume 2 of Russell and Whitehead's Principia Mathematica. So after 400 and some pages of a very, very meticulous step-by-step reconstruction of mathematics from this axiomatic starting point, they finally developed enough machinery to be able to prove the logical statement corresponding to 1 + 1 = 2. Okay, and then they did have a sense of humor about it. They remark, the above proposition is occasionally useful, and they say where else in the book they use it to derive other things. Okay, so. And now, actually, people like Wittgenstein, in his later years, I think, love to make fun of this sort of thing, okay? And, and indeed, it is easy to make fun of, right, on its face, right? Can you try to imagine someone who was really sort of on the fence about whether 1 + 1 = 2, right? They weren't quite sure, and then they studied Principia Mathematica, went through, they got to this page and said, oh, well, I guess it is 2 then, right? It's just, it's not very plausible. And I think, indeed, that is not the purpose at all of this sort of proof, right? If you didn't already know that 1 + 1 = 2, right, then no amount of, of axiomatic set theory and so forth is going to convince you. Okay, so, so I think the right analogy for what Russell and Whitehead were doing here is that, they were building a sort of computer, right? This was in 1910, okay? This was, before we had, electronic computers, okay? But they're building a logical sort of computer, okay? And, one of the things you can try when you have a new computer, right, or a new programming language or whatever, is you can try writing a program that prints hello world. Okay, now that by itself is not very impressive, right? You could have, just written hello world with marker on the screen. Okay, but the point is, you now have, you now did it, in a way which, using a machinery which is capable of all sorts of other things, which is, capable of playing Angry Birds or, or whatever, right? So, and indeed, likewise in this case, once you have this sort of general machinery for reducing mathematical proofs to a sequence of manipulations of formal symbols, it is useful for a lot of other things. Okay, I mentioned already, a major application of software verification. Okay, but in fact, this sort of program of axiomatizing mathematics, in the early 20th century, played a central role in launching the computer revolution itself. Okay, so to to do like intellectual history and, you know, in cartoon form, right? You know, Russell and Whitehead and Principia, you know, inspired Kurt Gödel, you know, to think about, you know, hey, you know, you could actually encode a proof itself as just a positive integer, or, you know, as we would say today, it's just a string of bits, okay? And you can reason about it as, you know, this mathematical object. You can then start asking meta questions about what can and cannot be proved, you know, what are the ultimate limits of some proof system. Okay, that, you know, work then directly inspired Turing, who then, you know, said, well, you know, once you've reduced sort of proof to this mechanical process, you could build an actual physical machine that could carry out the deductions for you. Okay, and you know, you know, Turing, as many of you know, was, you know, besides his work in logic, was involved in, you know, building some of the first computers to, you know, actually to break the Nazi naval codes during World War II. Okay, and so then this, you know, there is sort of a thread that leads from here to, you know, the stuff that we all have in our pockets and, you know, on our desks today. Okay, now, you know, sometimes the gap between proving and explaining, you know, has caused some actual mathematical controversy. So, you know, a famous example of this is the four-color map theorem, okay, which was conjectured in the mid-1800s, and which says that, you know, given any map, you know, in the plane or on a sphere, okay, you can always color each country one of four colors so that any two countries that share a border will be colored differently. Okay, if they share only a corner, they can be colored the same. So this was, you know, there were dozens of wrong proofs, you know, for more than a century. Finally, in 1976, it was proved by Appel and Hawken. Okay, but the catch is that their proof relied crucially on a computer to enumerate about 2,000 cases. Okay, and to check that, you know, for every one of these, you know, basically, you know, everything works out okay, and, you know, and therefore, you know, the creative part was to say that, you know, that checking these 2,000 cases is enough, right? And that, you know, to prove the general theorem. Okay, but, you know, this was, you know, something relatively new at the time, right? To, you know, that the proof, you know, is not just something that, you know, you can fully write, you know, even in a reasonable sized journal article, and that, you know, can be fully understood by someone. Part of the proof is to say, well, we ran this computer program and here was the result. Right, and in fact, you know, the result is too large in this case to even fit in the paper. Okay, but you know, this was the result. Okay, and so you know, so some people criticized this. They said, well, you know, what if the computer made a mistake? How do we know that it didn't? You know, and so forth. So you know, I think there's sort of an obvious response to that, which is if you're worried about it, well then, you know, just check again with another computer, right? Just, you know, write a different program, right? You know, and in fact, this has been done. So by now, the proof of the four-color theorem has been checked by different groups, you know, writing completely different computer code, checking it on different hardware. So at this point, I think that it's more, you know, we can be more confident that it's correct than sort of, you know, like a normal article, you know, probably the average article in a math journal that's only been checked by humans, right? And so I think that, you know, the certainty in the correctness is not really the right issue here because, you know, look, you know, humans make mistakes too, right? You know, yes, there could be a bug in the code. You know, there could also be a bug in your brain, right? But you know, the real issue is just that, you know, relying on a computer to help prove something, you know, means that you're taking away sort of the aspect of insight or understanding, okay? You're verifying that four colors always suffice, but at the end of the day, you understand, you know, a little more about why four colors suffice than you did when you started. Okay, and I think that's the aspect that many mathematicians really, you know, found unsatisfying about this. Okay, but you know, if you find that unsatisfying, then just wait for what's coming, okay? Because over the last 30 years, theoretical computer scientists, you know, I've shown, you know, here's some of the major players up there just to show you that they're real people, have, you know, taken the concept of proof sort of even, you know, much further away from explanation or from understanding than Frege and Russell and, you know, these other people at the turn of the century ever did. And in fact, you know, sometimes making the proof impossible to understand is actually the goal. Okay, and this is what happens, for example, in cryptography, where you actually design a proof protocol in order that that you can prove something to someone and not and guarantee that you won't have the person understand anything by the end of it. Okay, and I'll tell you about that. But in computer science, a proof can now be something which is probabilistic. It can be an interactive process between the prover and verifier. As if like a student in class is not just sitting passively, but is interrupting with questions, saying that doesn't make sense. Please clarify that. Okay, it can be an interactive process. It can be a quantum mechanical process, right? It can depend on what we think we know about the laws of physics. Okay, in general, a proof can be, I would say, compared to what it was before, sort of a more ephemeral process, something that convinces you, at least with very high probability, that the statement is true. Okay, but once it's over, need not leave sort of any trace by which you could then convince a third person. Okay, so proof can be dynamic, and can convince you, but then once it's over, then okay, then you might not know how to convince someone else. Okay, so as a warm-up to this, let's consider the power of random sampling. So just this week, right, the world got a dramatic demonstration of the power of statistical sampling methods. Where you could say that maybe the baseline of sort of political discourse was so low that that one guy, sort of Nate Silver, applying basically freshman level statistics to aggregating polls, was just perceived as like a deity or some sort of strange wizard. Okay, but but yes, indeed, you can make pretty good predictions, if you have enough sample data. Okay, and and the I guess the theoretically interesting thing about polling, right, is that the number of people that you need to poll, okay, doesn't actually depend at all on the total size of the population, right? It only depends on how accurate you would like your poll results to be. Okay, so if you want your poll to be accurate to plus or minus 1 points, then maybe you have to interview somewhere on the order of 10,000 people. Okay, but that's the same whether you're doing it in a country with 1 million people or a country with 1 billion people. Okay, so that's what makes sampling, I think, powerful in science and politics and and in fact even within math and computer science, sampling is an extremely powerful technique. So to give one example, let's say you want to prove an algebraic identity like the one that I've shown there. Okay, one way you can try to expand things out, prove by induction and so forth. Okay, a much cruder way to try to if you just want to know if the identity is true or not, right? You could try plugging in some random values and see if it works. Okay, now that you might say, okay, fine, but that doesn't sound like a proof at all. That just sounds like something a freshman would do, right? Or maybe a physicist or an engineer. Okay, but this is not something any self-respecting mathematician would do. Okay. But actually, if you know that on both sides you have a low-degree polynomial, okay, and you also know that your field of numbers is sufficiently large, like larger than the degree of the polynomial, then you can appeal to the fundamental theorem of algebra, okay, which tells you that if you've got two polynomials that differ at all, then they must differ on almost everywhere, on almost all of the points. Okay, so in other words, polynomials are a very powerful error-correcting code. Okay, and what that means is that if you just evaluate, an identity like that one on a few random points, and and the two sides are always equal, then you can be statistically, all but certain that actually, those two sides are equal as algebraic expressions. Okay, so. Because otherwise you would have found you would have been overwhelmingly likely to find a point where they differ. Okay, now if that's not good enough, if you're not yet certain enough, you can always repeat the test more times with more random values. Okay, and in fact, if you repeat, a couple hundred times, right, you can make the probability, that this test would err something like, 2 to the minus, 200 power, 2 to the minus 1,000 power. Okay, you can make it much more likely that, an asteroid would come through the ceiling and kill you, destroy the computer, than that this test would actually, fail to solve the problem. Okay, so, you can, okay, is this, mathematical certainty? Well, you can argue about that. Okay, but this is, certainly far more certainty than we use for making, life and death decisions and, all sorts of other areas of life. Okay, now one caveat here is all of this depends on the assumption that you really can choose numbers to test randomly. Okay, if your random number generator was biased, if there were some subtle conspiracy that was, biasing the random numbers you chose, then maybe the test would fail. Okay, and this has been, a very active research topic in computer science. What can you do with sort of, if you only, have a very weak source of randomness, or, you can't guarantee that your numbers are really random, but maybe only a little bit random, okay, and so forth. Because, that's, here, the proof, the mathematical proof is only as good as sort of your, a priori belief that these numbers that you were using for your test, are really random numbers. Okay, so now, upping the ante further in this sort of direction, you could also do, instead of a proof by statistical sampling, a proof by quantum mechanical sampling. Okay, so as many of you may know, in 1994, Peter Shor sparked a scientific revolution by showing that a quantum computer could quickly factor large numbers. Okay, and by the way, the record, just about a month ago, there was an announcement that a quantum computer has successfully factored 21 into 3 times 7, with high probability. Okay. So, so this technology, it, remains to be scaled up, okay? But, as far as anyone can tell, looks, perfectly consistent with the laws of physics, as we understand them. If it's not, that's even more interesting, right? But, Shor showed that, if you've got a, computer that, is actually based on the, the known laws of quantum physics, then it ought to be able to factor huge integers in a polynomial time. Okay, and now this is, a task whose presumed difficulty is the basis for almost all modern cryptography, right? Anytime, you order something from Amazon or whatever, right, your credit card number is protected by the belief that factoring is a hard problem, okay? Someone builds a quantum computer, that's no longer true. So that's Peter Shor. Those are some ions in a magnetic trap, which is one proposal for building a quantum computer. And when I did a Google image search for quantum computer, the thing on the right is one of the things that came up. So, I'm a theorist, I'm not an engineer. Maybe that's what they look like. Okay. But now, because this talk is about proof, one question that you could ask is, okay, but, suppose the quantum computer, produces an answer, right? Would you need to trust it, okay? How would you know it was the right answer? Okay, well, in the specific case of Shor's factoring algorithm, that issue doesn't really arise. Why? Because, if it spits out some prime factors, well, you can multiply them for yourself, by hand or with a classical computer. You can check that they really are the factors. Furthermore, there are fast classical methods known for certifying that a number is prime. Okay, so you could there you can check the quantum computer's work for yourself. If if it's not correct, then you can try again. Okay, but not all quantum algorithms necessarily share that property. Okay, so it could be that there are quantum algorithms where they produce an answer, but then the only feasible way to verify that answer is using another quantum computer. Okay, so with of course, you have this issue with any computer, right? How do you check its result for yourself? Okay, but with a classical computer, at least you can ask it to to generate a giant dump or a giant list of sort of every step that it took, which could then be printed out or given to someone else to check. With a quantum computer, the whole advantage of a quantum computer is that, if you have just like 1,000 particles, let's say, then in order to describe their quantum mechanical wave function, you would in general need a list of something like 2 to the 1,000th power complex numbers. Okay, so just to describe everything that was going on inside the quantum computer, classically, could require sort of more bits of information than could fit in the entire observable universe. Okay, so you would be in the situation where, if you believe the laws of quantum physics, and if you believe the competence of the computer designers, then, you can be confident in this mathematical assertion because, this quantum computer, its quantum state was measured and a certain answer was observed. Okay, and, it said, such and such is the answer to your problem. Okay, but you could never, even list all of the steps sort of that went into proving that, without sort of, filling up the entire observable universe. Okay, the only way to be certain of it is to, or the only way to check the answer is to try running it again with a different quantum computer. Okay, so today when theoretical computer scientists talk about a proof system, usually, in general what they mean is some sort of interactive game involving two players, Merlin, who's the omniscient but untrustworthy wizard, and Arthur, who is the skeptical and computationally bounded king. Okay, and there's a sequence of challenges and responses. Merlin can send messages to Arthur. Arthur can ask follow-up questions, and so forth. And and then at the end, Arthur, either says, "Okay, I believe the proof," or he says, "You're full of it, Merlin." Okay, so now there are two requirements, which are actually the same as in sort of traditional proof systems, but which get new interpretations here. The first is called completeness. It says if the underlying claim is true, then there must be some way that Merlin can behave in this interaction that causes Arthur to output "okay," at least most of the time. Okay. And then there's soundness, which says that if the claim is false, then regardless of how Merlin behaves, Arthur must not output "okay" most of the time. He must output BS most of the time. Okay, so if you have both of those requirements, well then if the claim is true, then there's some way Merlin can act so that Arthur will accept, and if Arthur accepts, then he's statistically very confident that indeed the claim is true. Okay, so let me show you an example of that because that's kind of abstract. Okay, so a classic example concerns the graph non-isomorphism problem. Okay, so suppose that Merlin wants to convince Arthur that two graphs are not isomorphic. Okay, which just means that these two graphs, no matter how you rearrange them, you can rearrange them topologically however you want, and that you cannot get the edges of one to line up with the edges of the other. Okay, in this case, I think it's pretty clear. These are both graphs with, 8 vertices, with 8 nodes, and with, degree, each one connected to 3 others. Okay, but you can see that they're different. Like the second one has triangles in it, and the first one doesn't. Okay, so there, I can give us I just gave you a simple argument for why these graphs are not isomorphic. Okay, now it might be that given any two non-isomorphic graphs, there's always such a simple argument you could give that would tell you, oh, well, look, this graph has this property and that one doesn't. Okay, but no one has proved that. That's an open problem. Okay, no one knows a general way, a general proof strategy, even for proving that with any reasonable sized proof that two non-isomorphic graphs are indeed different from each other. Okay, of course you could always just list all the possible permutations, of which there's n factorial, where n is the number of nodes. Okay, but that would be astronomically inefficient, if these graphs had, 100 nodes or 1,000 or whatever. Okay, but here's a very clever interactive solution that people realized in the 80s. Okay, so it's just Arthur picks one of the two graphs randomly. Okay, then he randomly permutes its vertices, and he sends Merlin the result. Okay, he then asks Merlin which graph he started with. Okay, so think about it. If the two graphs are not isomorphic, then Merlin should always be able to answer correctly. If they were isomorphic, then because Arthur is randomly permuting, he's just sending Merlin the same exact thing in the one case as in the other. Okay, and so Merlin, despite having unlimited computational power, it must get the wrong answer at least half the time. Okay, and so if you repeat this test, say 100 or 1,000 times, Arthur can become, again, statistically certain that the graphs are not isomorphic. Okay. Now, this sort of interactive protocol, is now known to have incredible power, okay? For example, there's this IP equals p-space theorem, okay, which says that, Merlin, via an interactive protocol like that one, could even, quickly convince Arthur, for example, that white has the win in chess. Okay, if indeed that's a true statement. Okay, so if Merlin comes claiming that white has the win in chess, right? How would you ever verify that? Well, you could play Merlin with him playing white. Okay, suppose he wins, then what? Maybe he's just a really good chess player, right? You could have him play Garry Kasparov, okay, again he wins. Okay, so he's a really good chess player, okay? But how do you know that he knows that that there is no possible strategy for black, that will beat his strategy, right? Okay, so it turns out that what you can do is you can actually convert chess to a different game. This one involving sums of polynomials over finite fields. So it's a less fun game probably. Okay, but in this transform game, it turns out that you can always do almost as well as it is possible for you to do simply by moving randomly at every turn, okay? So therefore, if you play this transformed game, and if you play randomly, and if Merlin wins, then you could be convinced that he also would have won in chess if you had played optimally. Okay, and you can be convinced that in fact white has the win in chess. Okay, now now you think about these protocols. Okay, so especially think about the graph non-isomorphism protocol, right? It has another amazing property besides its efficiency, which is you think about it. Arthur, he became convinced that these two graphs are different from each other. Okay, but he learned nothing whatsoever about why the graphs were not isomorphic, right? In fact, all Merlin ever told him was, here's which graph you, Arthur, started with. Okay, but Arthur already knew that. Right? He picked it. Right? So, it's kind of, it's like someone says that they can tell Coke from Pepsi, right? And so, you give them one and they tell you which it is. Okay, you have, if you'd merely believed the person in the first place, right, then you could have simulated the entire interaction for yourself. Okay, so in fact, Goldreich, Macaulay, and Vigderson showed that under plausible cryptographic assumptions, every formal proof can likewise be converted into a zero-knowledge proof. And furthermore, here the prover need not be a wizard, but can just be an ordinary person who knows the original proof. Okay, so the key to proving that is to start with a so-called NP-complete problem. Okay, which is this famous class of, very hard, apparently very hard combinatorial problems. Okay, and a good example here is the Hamilton cycle problem, which is the problem where I give you a graph, like that one, and I ask you, is there a tour that visits each node exactly once? Okay, so in this case, you may have to stare at it, then you'll say, yes, indeed, there is one. There, it's easier when you highlight it, you see, right? So, okay, so now, what the NP completeness of this problem means is that a solution to it can encode a formal proof of the Riemann hypothesis or of any other mathematical theorem you want. In other words, it is possible to design a graph. It'll probably have some billions of vertices, but it could be stored in a computer, right? And, it will have the property that this graph has a Hamilton cycle if and only if there is a proof of the Riemann hypothesis in, let's say, ZF set theory with, let's say, 10,000 symbols or fewer. Okay? And furthermore, if someone finds that Hamilton cycle, then from that they could read off a proof of the Riemann hypothesis. Okay? That is what NP completeness means. Okay? But that's not even the interesting part here. Okay? This is stuff from the early 70s. Okay? So now, in order to get a zero knowledge proof, here's what you could do. You could say Merlin randomly permutes the nodes of the graph. Okay? Then for each pair of nodes, he sends Arthur a locked box, inside of which he's written whether or not those nodes are connected by an edge. Okay, so now that, with the boxes in his possession, Arthur can do one of two things, by like flipping a coin, let's say. Either he can ask Merlin to unlock all the boxes and also show him the isomorphism, or the permutation between the new graph and the original graph. Show him how he permuted the vertices around. Okay, and if he does that, then he'll make sure that there's no funny business, that Merlin really is following the protocol correctly, right? He really did just permute around the original graph and do nothing other than that. Or the second thing that he could ask is he can ask Merlin to not permute anything, but only unlock the boxes that correspond to a Hamilton cycle. So, then Merlin would unlock these 4 boxes, let's say. Okay? In the second case, Arthur, sees that, yes, the graph must have had a Hamilton cycle in it. Okay, but because the graph had been randomly permuted, he has no idea, what Hamilton cycle that actually corresponded to in the original graph. All he sees is that there is a Hamilton cycle. So, so this, then, and then you can repeat it, if Arthur wants to be more confident with a new set of lock boxes. Okay, and now if you want to implement this over the internet, then you simply replace the lock boxes by encryption. Okay, and opening the boxes by decrypting the encrypted messages. Okay, this has been, it's conceptually interesting. It's also been hugely practically useful in modern cryptography because, it lets suspicious agents prove to each other that they're carrying out a protocol correctly without revealing the secret information on which those proofs are based. Okay, and one example application of this, which might be, timely to mention, is electronic voting. Okay, you could, it's known today that, you could have voting over the internet in a way that, you can be confident, first of all, that your vote has been counted, but also that your vote will remain anonymous. Okay, and this is called secure function evaluation. It depends crucially on these sorts of zero-knowledge protocols for NP-complete problems. Okay, in order to do it practically, you would still have to convince, even if we know that it's secure, you would have to convince the person on the street, that it's secure. So I think paper balloting paper ballots are probably better for the foreseeable future. But, in principle, this would work. Okay, so, Renaissance court mathematicians were terrified of rivals stealing their secrets. I mean, Galileo once, ensured his priority for the discovery of Saturn's moons by sending Kepler a coded message, which was that thing, right? And so, another application of this, let's say you've proved the Riemann hypothesis, but you're paranoid that someone will steal the proof if you reveal it to them. You could actually use this protocol in order to convince the world that you have a proof of the Riemann hypothesis and not reveal anything about it. So it would be like, theoretical computer science surging forward into the 1500s when, court mathematicians would be challenging each other to duels and stuff rather than just publishing their proofs. Okay. So, one other famous NP-complete problem, and then, I'll wrap up, is a problem of 3-coloring a graph. So, color each node one of 3 colors so that every 2 adjacent nodes are colored differently. Okay, now, we could suppose that 2 Merlins claim that they know how to 3-color a certain graph. Suppose that Arthur will get $1 billion if he can prove they're lying, but he's only allowed to ask them for the color of 1 node each. Okay, what could Arthur do in this situation? Now, here's what he can do. Now he can put the 2 Merlins in separate rooms where they can't talk to each other. Okay, so it's like a police interrogation of 2 witnesses. Okay, and then he can either pick a random node and ask both Merlins for its color, and and they better give the same answer. Okay, or he can pick 2 adjacent nodes and ask Merlin 1 the color of the first and Merlin 2 the color of the second, and make sure and check that they give different answers. Okay, and if you work through the logic, if the graph is not 3-colorable, then the Merlins must fail this test with some appreciable probability, which will be, like 1 over the number of edges or something. Okay, so this is called a multi-prover interactive proof system. And now, it doesn't sound very impressive yet. Okay, but pushing this further, it was discovered that you could actually make the probability that Arthur will catch the Merlins lying, because of their failure to coordinate with each other, you can make it actually a constant, independent of the problem size. That then led to the PCP theorem, probabilistically checkable proofs theorem, which is one of the crown jewels of theoretical computer science. It says that any formal proof can be rewritten in an error-correcting format in such a way that the validity of the proof can be checked with high statistical confidence by looking at only, let's say, 10 or 20 random bits of the proof. Okay, in fact, a constant number, completely independent of the size of the proof. Okay, and this is then implied that all sorts of for various NP complete problems that it's hard even to find an approximate solution. That was a major application of this. But now a recent realization, here's where it really gets amusing, okay, is that although this gives you a sound and complete proof system, okay, because the Merlins are in separate rooms, they can't talk to each other, okay, even if they can't talk to each other, if they shared quantum mechanically entangled particles, right, which how do you know that they don't, right, then by making suitable measurements on their particles, they could sometimes coordinate their responses in such a way that they would always pass the test, okay, that they would convince Arthur that the graph is three-colorable, even though it isn't. Right, and this is directly related to the famous Bell inequality, right, which says that, although there's no faster than light communication, there is this sort of non-local ability to win certain games, and this is, in fact, a perfect example of it. Bell could have phrased his discovery in terms of multi-prover interactive proof systems, to be anachronistic. Okay. On the other hand, just this year, there was a breakthrough by Tsuyoshi Ito and my postdoc, Thomas Vidic, who have proved that every multi-prover interactive proof system can be immunized against the presence of entanglement. Okay, so it is a problem that you can ultimately solve, but it took a lot of effort. Okay, so summary. With Frege, Russell, Gödel, and so forth, proofs became mathematical objects in their own right. Sequences of symbols that can be verified by a machine and that no human necessarily has to understand. Today, theoretical computer science has taken the separation between verifying and understanding, even further than, Russell and Gödel dared to, maybe, by making proofs probabilistic, interactive, zero knowledge, quantum mechanical, and so forth. Now, what's the point of doing that? Well, Russell's redefinition of proof helped to bring us the computer age. The modern redefinitions, I think, help to bring secure electronic commerce, and all sorts of other, profound insights about the nature of computation that we wouldn't have gotten otherwise. But a central irony here is that all of these amazing discoveries about proof relied themselves on traditional understanding-based proofs, right? I didn't give you formal sequences of symbols, right? To tell you why these protocols worked. I just explained to you, here's why they work, right? And so, in theoretical computer science, we sort of don't practice what we preach. Right, we talk about proof as this purely formal thing, this sequence of symbols that could be mechanically verified or, probabilistically verified or whatever. But when it comes to what we actually do, we still seek explanation and understanding. Okay, and so, a big question here would be, will we ever have a mechanistic account of explaining and understanding in the same sense that we now have a mechanistic account of proving and verifying? Okay, so thank you.